When you take a high school physics class, you spend what feels like a month on these 5 equations, and then another month adding this equation to them. So you spend what feels like an inordinate amount of time on 6 equations, but really you only need these 2. So in this video, I want to talk about why I prefer using these 2 instead of these 6. First of all, having fewer equations means there is less that you have to keep track of. There's less guesswork. When you solve a problem using these 6 equations, you spend most of your time hunting and searching for the right equation to use. You've got to look at the information in the problem. You've got to take down what you know, what you don't know, what among what you know that you are looking for, and what among what you know that you don't care about. Also that you can select the one magic equation that you can plug numbers into and get a number out. On the other hand, with these 2 equations, you always know what equations to use. It's always going to be these 2. It's never going to be these 2 plus some random third thing that you've got to bring in. It's always going to be these 2 because these 2 equations contain all the information that these have. These are redundant. If you solve a problem using these equations, you're carrying around extra mathematical baggage. These are sleek, they are efficient, and they contain everything that you need. Another way to think about it, let's suppose you have a problem where you need to solve for the final velocity. Well, in these 2 equations, you've got 2 of them that start with VF equals. And so it's very tempting to just start plugging numbers into that first one. Oh, VF equals, well, I just plug in VI plus AT. Oh, wait. I don't have acceleration, or I don't have time, or I don't have initial velocity. Oh wait, there's a second one that's got VF squared equals. Well, I know how to take a square root of both sides. Oh, but again, what if I don't have the magic set of information that's on the right-hand side of the equation? Because VF is lurking in 2 more equations, this one and this one. It's hiding out in there. And so it could be any one of those 4 equations to solve for V final. It's a very long winnowing process to figure out which equation to use. Again, on the other hand, with these 2 equations, you're going to use these 2. You're going to have a V final in that delta V, because that's going to be V final minus V initial, and you're probably going to have a V final in this Vx here, because this is usually going to be the average, V final plus V initial divided by 2. That's not a physics formula, that's a math formula, that the average of 2 numbers is add them up, divide by 2, right? And so I know which equations to use here. I'm always going to use these 2, whereas for these folks, I'm always left guessing. Second reason I prefer these on the left is that these equations actually tell you the story of what's going on in the universe. These are framed explicitly in terms of a cause on the right-hand side and an effect on the left-hand side. The causes, the right-hand side, for example, for delta Vx, that first equation, a change in velocity is an effect that is caused by 3 things. A net force acting in the x direction, an amount of time that that force acts on, and the mass of the thing that is moving. It is effect on one side and causes on the other, and those causes lead to the effect. Second equation has 2 causes. It's got the velocity that the particle, the car, the whatever is experiencing, and the amount of time it moves produces the effect of a change in position. Causes on one side, effect on the other. These equations, they've got causes and effects mixed together all over the place. The first one is in pretty good shape, right? You end up with a V final over here. You started with a V initial over here. You have an acceleration through that amount of time, and those 3 factors go into the V final. Okay, yeah, that makes sense. The second and third one also kind of makes sense in terms of cause and effect, but the third one is already getting a little bit messy because time is in there twice, right? So I've got time influencing distance through V initial, but then it's also influencing distance through the acceleration. Well, what happens if my acceleration is negative, right? Does that mean time is causing distance to increase, but also causing it to decrease? Like, how does that work? The fourth one's even more confusing because it's got a time and then a negative time squared. What? like what is the relationship between distance and time there? It's really unclear. And then the last one has a v final affecting the distance, and that v final is also an effect? Like, how is this working? Where are all these changes? Where is this chain of cause and effect coming from? See, with the equations on the left, I can tell a story. I can tell a story about how there was a force that acted for a certain amount of time on a mass that produced a change in velocity. And then I can tell a story about how there was a velocity carrying something along for an amount of time that caused its position to change, caused it to move. These on the right, they don't tell a story. These on the right serve one purpose and one purpose only, and that's to crank out a number at the end. And if there's one thing we've learned from centuries of teaching physics, it's that crunching numbers doesn't tell you what actually happened. It doesn't actually solidify in your brain what the physics actually means. Third reason, you might have noticed that these equations over here have an extra variable compared to the ones over here, right? They've both got a distance. Here it's traditionally called d. Here it's called explicitly delta x to remind you that these things can be vectors, that they can go in multiple dimensions. But over here, you have this extra thing called a, the acceleration. Acceleration is something physicists really don't use that much because it's really not necessary. I mean, think about it. What does acceleration do? Well, it produces a change in velocity. Okay, where does it come from? Well, it comes from a force right here, which you usually don't even get until a month or two after you've had these equations. So you have these equations floating around for about a month, and acceleration is just sort of the end-all be-all, and then later they tell you, oh, by the way, acceleration comes from a force. Well, then why do you even have acceleration? It comes from something and then produces something, but it itself, like, there's no actual pedagogical or cognitive value to it. You might as well just link the force directly to the change in velocity, right? If you take that top equation here and you rearrange it, you get F net equals m delta v over delta t. Well, that's exactly what you have over here. F net equals m delta v over delta t. So why bother with this mediator? Why bother with having another quantity in the problem? That's only going to serve to confuse yourself. Really, I can only think of two cases where it's helpful to think in terms of acceleration. One is one problem in advanced upper-level electromagnetic theory where you need the self-exerted force on a particle, a charged particle, when it accelerates. In an intro physics class, you're probably not studying that, so you don't need that. The only other case is when you talk about g-forces, when you talk about force on a human body as a proportion of its weight. It's helpful to talk then in terms of your acceleration in terms of g's, because we have evolved on this planet with a nice uniform constant gravitational field of around 9.8 newtons per kilogram. And it's helpful for us to express our acceleration of those terms because our bodies can only handle so many g's before we start experiencing bad side effects. And so that's helpful. But again, you can also express that in terms of the weight. You can express that in terms of a force over here and talk about the net force you are experiencing in relation to your weight, mass times gravitational field. And so these equations, they cut out an unnecessary quantity that you don't need mucking up your physics. Reason number 4, we already talked about this a little bit, but I have these equations in separate boxes. I have F equals ma hanging out all on its own. Because in a traditional curriculum, like I said, you spend what feels like about a month. And I'm estimating a month. I might be misremembering that. So please, if it's less than a month, please correct me. But it sure did feel like a month in high school physics that we spent on these equations, and acceleration was the end of the story. And then we had to go back and review them when F equals ma showed up. So why are we treating kinematics twice? Why should you have to learn the exact same thing twice when you can just introduce it once here and directly introduce forces from the get-go, directly connect the root cause to the effect? And lastly, you can do more with these equations, right? The only thing you can do with these equations really is plug some numbers in and get some numbers out. And there's really only so much cognitively you can get with that. Whereas these, I can turn these into a story. I can turn them into a description. I can use these better in the lab because my lab is explicitly framed in terms of causes and effect. And these, as you've seen on this channel, are the framework you can use to run a numerical simulation. You can plug these into a computer. Instead of delta t being the amount of time for the entire trip, you can make delta t a very small step so that you're dividing your trip up into several steps. You can get a computer to treat it. Whereas these, they don't work well in a computer program, right? Because you have 3 equations for distance. How am I going to calculate distance if I've got 3 of those there, right? I've got to basically reduce them down to these 2 to get a simulation running. So that's why I prefer using 2 equations instead of 6. If you're in my class and you want to use these 6, you are absolutely welcome to. If for whatever reason these work better in your mind than these 2 do, like, I don't understand that, but that doesn't make it invalid for your experience. You are certainly welcome to. But the thing is, when you use these, you've always got to put in this F equals ma, because if you're not using force, you haven't really solved the problem. You haven't really offered an explanation of connecting the causes to the effects.